The sub-Riemannian Heisenberg group is the main example of sub-Riemannian geometry that is actually not Riemannian. Such a geometry is connected to the solution of the isoperimetric problem on the plane, and has also a formulation in terms of contact geometry. In this video, or sequence of videos, we will present the geometric model of the sub-Riemannian Heisenberg group and identify some of the properties that we will see later and study in arbitrary Carnot groups. Since the topological dimension of the Heisenberg group is 3, we will be able to visualize the shape of sub-Riemannian spheres and sub-Riemannian geodesics. The isoperimetric problem is the problem in which, given a length, one has to look for the maximum area among those domains with that fixed length as perimeter. We will be interested in a variant of the standard isoperimetric problem, which is called the Dido problem. Dido, according to ancient Greek and Roman sources, was the founder and first queen of Carthage. In modern terms, in modern days, it's called Tunisia. She's best known for the account given by the Roman poet Virgil in his book Aeneid. Indeed, in this epic poem, it is narrated that King Iarbas was persuaded by Dido to give her a piece of land on the African coast to settle. This land would have been as much as Queen Dido would have encaptured with a leather string, using also possibly the coastline. So with the coastline and having a length, it's easy to maximize the area, and the solution is half of a circle. Half of the circle is the solution of Dido's problem. Let's give a mathematical model for the isoperimetric problem. So, mathematical model for the isoperimetric problem. So on R2, we have the area form. It's denoted with vol, which in coordinate x and y is just dx wedge dy. Now we observe this fact that the area form is the differential of one form, which is the differential of the one form, let's call it alpha, which is 1/2 x dy minus y dx. Okay, so what I'm saying here is that if I do the alpha, then I have 1/2 dx dy, differentiating this part. Now I differentiate this other part, plus dy dx. Better put wedges on here. Now this is a minus, and now I invert these two and I get twice the same thing with a half in front. I get dx wedge dy, which is the volume 4. Now let's see what happens if we apply Stokes' theorem. So if we have now a curve that let's call it gamma, that encloses some area, some region called D gamma. Then, by Stokes' theorem, we have that the that area of this region, which is nothing else than the integral of the volume form vol over D gamma. Now, we said vol can be seen as the differential of alpha. Now, by Stokes is used here, and we get now that this is the same of integrating over the boundary the original one form. Okay, so what we understood is that to calculate the area of the alpha, it's enough to integrate along gamma the one form alpha. Now this if gamma was a closed curve. Now what happens if gamma is not a closed curve? So what about if gamma has different endpoints? And now we notice something that let's say that the curve gamma of zero is 0. Now what we do, we now consider the straight line going from gamma 0 to gamma 1. Say the curve was parameterized between as a curve from on 0, 1. Now what we see is that this vector is radial and annihilates the one form alpha. In fact, one can also write alpha in the form still 1/2 r theta d theta in exponential polar coordinates. So you see the component along the r is 0. So which means that integrating alpha along a line, a radius starting from the origin is 0, which means that integrating alpha along gamma or along gamma together with the straight line is the same thing, okay? Which means that integrating on gamma alpha, it gives the area of the area enclosed by gamma and the straight line connecting 0 to gamma 1. This observation let us conclude that if gamma is a smooth curve starting from the origin that is not necessarily closed, then the integral over gamma of alpha expresses the sign area enclosed by gamma and the segment connecting the origin to the final point of gamma. Yeah, like see this picture. And therefore, we rephrase Dido's problem as the problem of finding those curves gamma that maximize the integral over gamma of alpha, having fixed the length of gamma, namely the integral over gamma of ds. The ds is so is in this way we can express the length of the curve as the integral of it with respect to the arc length element ds. And let me recall that alpha is 1/2 of x dy minus y dx. The isoperimetric problem admits a reformulation as a problem of finding the shortest curve in a three-dimensional geometry. The curves should satisfy a condition which is called contact condition, namely to be tangent to a contact distribution. And the shortest curve in this, therefore, sub-Riemannian geometry will project on the plane as the solution of the of Dido's problem.
We start with a curve, sigma, in R2. So sigma t has coordinates x, t, y, t. And let's say that x of 0 is equal to y of 0 is 0. So the curve starts from the origin in the plane. Now we want to lift this curve in the three-dimensional space. So initially it was into R2, now we want to go into R3. So we have to get 1/3, the third coordinate. And we do it like this. So for lifting, we define the third coordinate as, so let's call it z of t. And what is this curve? So if the curve at time t is at reached a point, then we consider the sine area enclosed by this region. Why am I talking about sine areas? Because if a curve is moving clockwise, then the area of the form that we were integrating is going to represent exactly the area as a positive value. Said when the curve goes clockwise, then the sine area, will be a negative number. And if the curve is sometimes going clockwise, sometimes counterclockwise, we are going to have in some part positive area, some part negative, and the sine area is the sum of this. Okay, so going back to the definition of the sine area, so this is expressed as the integral along the curve sigma restricted to, or sigma of 0, 1, yeah, restricted to 0 t of the form alpha. So this was the definition of alpha is 1/2 of x dy minus y dx. Okay. Now, what does it mean to integrate one form along a curve? This means you have to plug in the coordinates of the curve and their derivatives. So this means the integration between 0 and t of 1/2. So x is the first coordinate of the curve. So it's xt, and then dy, the derivative of y. Okay, I cannot call the variable t because t is the endpoint of the integration. Let's call it s. So y dot, with dot I am indicating the derivative. That minus y of s, x dot of s, this is integrated in the s. Okay, so now let's differentiate this this equality. So z is the integral, and now let's take the derivative respect to t. Differentiating in t, we get, okay, z dot is equal 1/2 of x y dot minus y x dot. Okay, so now we see this object here can be seen as a one form. Let's give a name to this one form. So let's set let's call it xi to be dz minus 1/2 of x dy minus y dx. Okay, so now this has become a one form in R3. One form in R3. So now we can say that the forms, the lifts of the curves, the planar curves that we had, were satisfying this equality, right? In other words, they were annihilating this one form. So let's repeat what I said. So now consider a curve gamma, okay, say in coordinates gamma 1, gamma 2, gamma 3 from 0, 1 into R3, starting at the 0 of R3, then we have that such a curve lifts to a planar curve, is the lift of a planar curve if and only if the kernel, the derivative is in the kernel of this one form. Okay? We have that gamma is a lift of some sigma, which actually then sigma is actually the first two coordinates, if and only if gamma dot is in the kernel of this one form, which is the same as saying that xi at gamma dot is equal to 0, constantly equal to 0. Let's give a name to this very special one form. Definition. We call the differential one form so xi is defined as dz minus 1/2 x dy minus y dx, which actually in cylindrical coordinates, is actually equal to dz minus 1/2 r squared d theta. So it's cylindrically symmetric. So we call such a one form the standard contact form. Remember that we are interested in the equation gamma dot is in the kernel of xi. So now, let's try to study what is, from the geometric point of view, this kernel. Okay, and actually every whenever you have any one differential one form, so if xi is okay, never vanishing differential one form, on R3, then at every point x, y, z in R3 we can associate, we have a two-dimensional subspace of the tangent let's call it T, X, Y, Z, R3 of R3 at X, Y, Z. Since we are in a vector space, then the tangent of the vector space is canonically isomorphic to the vector space itself. Now, what is this two-dimensional subspace? Let's call it delta at X, Y, Z. So this is a subspace, and is defined as the kernel of Xi at the point X, Y, Z. What does it mean? This means these are all the vectors in R3. So we can write V1, V1, V2, V3, on which Xi, point X, Y, Z, V1, V2, V3 is equal to 0. In the case of, for the contact structure, standard contact structure, then this is the V1, V2, V3, such that V3 is equal 1/2 of X V1, V2 minus Y V1. Right? This is the form Xi. So these are the values, the variables of the and the manifold where we are, and then these are the components. These are the element, the differential that takes the elements of the vectors. So we have this quantity here. A little bit of observations. So first of all, if we have a form that never vanishes, then not all vectors are sent to 0, right? And since this is a linear map, the kernel is at least two-dimensional. So, so for any X, Y, Z, this space delta is a two-dimensional subset of the tangent. So we should think that this is an element in the tangent at X, Y, Z of R3. Moreover, these planes, we can call it plane field, have the property that in the case of the contact structure, you never have the vertical lines, because if this is non-zero, then V1 and V2 cannot be both 0. Okay, so the picture one should have in mind is that you have the z-axis that is not in this plane field, and at every point you have a tangent plane that is whose rotation in space is changing according to the point X, Y, Z. Okay, so let's write that. So geometrically, delta is a rank 2 plane field on R3. Okay, so now we want to put a metric on this on each of these planes. Namely, we want to say how long are vectors that are tangent to this plane field. Now we do like this. So given vectors, so V equal V1, V2, V3, and W, W1, W2, W3 in R3, we consider the linear product. So the product between V and W is just V1 W1 plus V2 W2. Now see, it's not the standard one because we don't have V3 W3. Okay, this is not a scalar product. Okay, but it's a linear map. Okay. Now what we want to see that because in delta we never had the z-axis, then the restriction of this linear map defines a positive definite inner product, a scalar product on delta. Okay, so what I want to say is that this map defines an inner product. Let's call it scalar product. Scalar product on each delta x, y, z. So in each of these space, we have defined a scalar product. Now, we can also see the scalar product as really a scalar product of the whole space and then restrict it to each plane. Actually, we'll do something better. We will really see that there is a frame of the three-dimensional space for which two of the vectors, one is transverse, and the other two instead give an orthonormal basis for each of the tangent plane or plane field. Okay. Note here, there is a frame for delta that is orthonormal. In fact, let's consider the following vector fields. So x, which I will still use coordinate little x, little y, little z, is dx minus 1/2 y dz. Y is dy plus 1/2 x dz. Let's consider z also equal dz. I hope the notation is clear that dx is another text is denoted like this. Okay, it's just a notation. So what we could do, we can declare these to be an orthonormal frame. So first of all, let's see really that they are linearly independent. Okay, so of course that these two are linearly independent because the x component, xy component are different, and now you see that this object here is linearly independent from the other one. In fact, like if you sum for any point x, y, and z, you can sum this one to cancel, and you have the standard frame. Okay, so this is a frame of R3, and we can think that this frame is also giving a Riemannian metric. But now what I want you to notice is that X and Y is a frame for delta. Okay, let's clarify this. So of course, like these are two linearly independent at every point. So at every point they find a plane. Let's say that they find the same point of this plane field at that point. Okay. Now, what we could do, since we can write d over dx equal to x plus 1/2 yz, and d over dy as y minus 1/2 x dz, then you can write a vector v in coordinates v1, v2, v3, v1, v2, v3, which means actually v1 dx plus v2 dy plus v3 dz. Okay. Yes. So this is dx. Then we can substitute and get that this is v1 x plus v2 y plus, now there is v1/2, so this one v1/2 times 1/2 times y, then let have minus still v2 over 2x plus v3 z. Okay, so what we have done, okay, we actually wrote every vector in R3 as a linear combination of x, y, z, right? So this is another proof that x, y, and z are a frame. Okay, now what does it mean that this vector is in the distribution in the plane field given by delta? This was exactly that this was 0. Okay, so conclusion: V is in delta x, y, z if and only if V is equal v1 x plus v2 y. In other words, it's in the frame given by x and y. Moreover, when V is in this plane field, then the length of it is exactly v1 of the Euclidean length of the vector v1, v2. So now it means that the scalar product that we have is really given by x and y as orthonormal frame. Okay, so now let's look at curves whose derivative have this property. So in contact geometry, a curve gamma is called Legendrian. Later we will actually use other terms like horizontal curves or admissible. We use the term horizontal or admissible when we will have things that are more general than the plane field given by the contact distribution. So it's called Legendrian, if the derivative of the curve is in the horizontal distribution, in the contact distribution. So x annihilates gamma dot. In other words, gamma dot is tangent to the gamma is tangent to the distribution. Okay, now for a Legendre curve, we can define the length. So if gamma is Legendre, we can define the length of gamma with the scalar product. And what is so this is the length with respect to xy as orthonormal frame. However, for what we saw before, the length of this vector is equal to the length of the projection onto the plane. Right? It's only the two coordinates of the vector that are important. Okay. So let me write it as that. So this length here coincide with the Euclidean length of gamma of the projection of gamma on the xy plane. So just forgetting the third coordinate. Now that we have curves, we can measure length of these curves. We can define a distance. So define a distance function which sometimes is also called contact distance. So defined, let's put a C for contact. The distance between P and Q is defined as the infimum of all those lengths of curves that are Legendrian and go between P and Q. Now, when points P and Q, which these are points P and Q in the three-dimensional space, but we can look at the projection of them in the plane. And now, the fact that these curves are lift of the curves by the area, by the sine area, we know that there are several curves that connect P and Q, right? They just have to be curves that connect in the projection whose area, the sine area, is equal to the difference in the height of these 2 points. Okay, so let's clarify why Legendrian curves exist. Curves exist between any 2 points. Okay, so this is going to be very important. Let's call it a crucial fact. Every pair of points in R3 is connected by a curve that is Legendrian with respect to the standard contact for Xi. Okay, let's prove it. Okay, indeed. So first of all, if you have 2 points, we can just we can assume that one of the 2 points is the origin. Right? Then you can just join 2 curves. So to connect 0, 0, 0 to x, y, z, it is enough to take a planar curve sigma that goes going from 0, 0 to x, y. Of course, we have many. We can just create a straight line, but we cannot take in. We have to pay attention to what is z, and with the property that the sign area enclosed by sigma and the final segment is exactly z. So enclosed by sigma and the segment from 0, 0 to x, y is exactly z. In other words, to connect to a point x, y, z, what we have to do? We have the point 0, 0. We have the point x, y. Okay. If you take the straight line, we have enclosed area 0. So if z was 0, we can take this curve. Otherwise, we cannot. But it's pretty clear what to do. Just take a curve. You have a family of curves, right? And the more you move this curve, the more area you enclose. Of course, one has to pay attention, because if you go this way, the sign area is positive. So if the sign area is negative, one should go in the other direction. So these curves here have negative area. These other curves have positive enclosed area, right? But we can reach any point, any value z, and the lift of the curve that is encapturing area z is a curve connecting 0, 0, 0 to x, y, z. And remember that the length of gamma with respect to our scalar product is the same of the length of sigma. Okay, and therefore this was exactly the length that we had to fix in the problem of Dido's problem. So in Dido's problem, we had sigma has given length, and we want to maximize z. But this could be seen as a dual problem. Like, let's say z is given, can you then minimize sigma, right? But because we know the solution of the isoperimetric problem in Dido's problem, what we will be able to do, we will be able to write the precise curves that reach the minimum for this set. Namely, we will write the geodesics with respect to this distance.
If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on sub-Riemannian geometry, please subscribe to the channel clicking below. Bye.